Chapter 1.4.1.3 Sidecar Containers. In Kubernetes v1.29 beta, sidecar containers are secondary containers that run alongside the main application container within the same pod. These additional containers are used to enhance or extend the functionality of the primary app container by providing services such as logging, monitoring, security, or data synchronization without altering the primary application code. Typically, there is only one app container in a pod. For instance, in a web application that needs a local web server, the local web server would be a sidecar container, while the web application itself would be the app container. Sidecar containers in Kubernetes. Kubernetes allows for the implementation of sidecar containers, a type of container that remains running after a pod startup. These sidecar containers are independent from other init containers and the main application container within the same pod. By enabling the Sidecar Containers feature gate, you can specify a restart policy for containers listed in a pod's init containers field. This allows you to start, stop, or restart sidecar containers without affecting the main application container. Additionally, you can run a pod with multiple containers that are not marked as init or sidecar containers if they are required for the overall function of the pod. This is useful for supporting older versions of Kubernetes that do not have a container-level restart policy field. For example, a deployment can be created with two containers, one of which is a sidecar. Sidecar containers and pod lifecycle. An init container with a restart policy set to always will start and run throughout the life of the pod, helpful for running supporting services separate from the main application containers. A readiness probe for this init container will determine the pod's ready state. These init containers benefit from the same ordering guarantees as regular init containers, allowing for complex pod initialization flows, mixing sidecar containers with regular init containers. Sidecars defined within init containers continue running after starting, important when there are multiple entries in .spec.init containers for a pod. Once a sidecar-style init container is running, the kubelet then starts the next init container in the ordered list. Jobs using sidecar containers in Kubernetes-style init containers do not prevent the job from completing after the main container finishes. Differences from application containers. Sidecar containers run alongside app containers in the same pod, providing supporting functionality without executing primary application logic. They have independent life cycles, allowing for separate starting, stopping, and restarting from app containers. This enables updating, scaling, or maintaining sidecar containers without affecting the primary application. Sidecar containers share network and storage namespaces with the primary container, allowing for close interaction and resource sharing. This co-location enhances efficiency and collaboration between sidecar and app containers within a pod. Differences from init containers. Sidecar containers are additional containers that work alongside the main container, providing extra services and functionality. They run concurrently with the main application container and can be started and stopped independently. Unlike init containers, sidecar containers support probes to control their lifecycle. They can interact directly with the main application containers and share the same network and volumes. Init containers cannot exchange messages with app containers in a pod, as they stop before the main containers start up. Resource sharing within containers. The text explains the order of execution for init, sidecar, and app containers in a Kubernetes pod, detailing how resource usage is determined. It states that the effective init request limit is the highest of any particular resource request or limit defined on all init containers. If no limit is specified for a resource, it is considered as the highest limit. The pod's effective request limit for a resource is the sum of pod overhead and the higher of the sum of all non-init containers, or the effective init request limit. Scheduling is based on effective requests limits, allowing init containers to reserve resources not used during the pod's lifespan. The QoS tier is determined by all containers within the pod, and quota and limits are applied based on the effective pod request limit. Linux C groups allocate resources based on the effective pod request limit